Anytime you have an equation, like this one, that has variables in the exponent, logs are the tool of choice for getting those variables down where you can solve for them. In this video, I'll do a few examples of solving equations with variables in the exponents. For our first example, let's solve for x the equation 5 times 2 to the x plus 1 equals 17. As my first step, I'm going to isolate the difficult spot, the part that has the variables in the exponent. In this example, I can do that by dividing both sides by 5. That gives me 2 to the x plus 1 equals 17 over 5. Next, I'm going to take the log of both sides. It's possible to take the log with any base, but I prefer to take the log base 10 or the log base e for the simple reason that my calculator has buttons for those logs. So in this example, I'll just take the log base 10. So I can omit the base because base 10 is implied here. And that gives me this expression. As my next step, I'm going to use log rules to bring down my exponent and multiply it on the front. It's important to use parentheses here because the entire x plus 1 needs to get multiplied by log 2. So that was my third step using the log rules. Now all my variables are down from the exponent where I can work with them, but I still need to solve for x. Right now x is trapped in the parentheses, so I'm going to free it from the parentheses by distributing. So I get x log 2 plus log 2 equals log of 17/5. Now I will try to isolate x by moving all my terms with x's in them to one side and all my terms without x's in them to the other side. Finally, I factor out my x, well, it's already kind of factored out, and I divide to isolate it. So I'll write out what I did so far. I distributed, I moved all the x terms on one side and the terms without x's on the other side, and then I isolated the x by factoring out and dividing. We have an exact solution for x. This is correct, but maybe not so useful if you want a decimal answer. At this point, you can type in everything into your calculator using parentheses liberally to get a decimal answer of about 0.765. It's always a good idea to check your work by typing in this decimal answer and seeing if the equation checks out. This next example is trickier because there are variables in the exponent in two places with two different bases. Our first step is normally to clean things up and simplify by isolating the tricky stuff. But in this example, there's nothing really to clean up or simplify or no way to isolate anything more than it already is. So we'll go ahead to the next step and take the log of both sides. Again, I'll go ahead and use log base 10, but we could use log base e instead. Next, we can use log rules to bring down the exponents. This gives me 2x minus 3 in parentheses, log 2 equals x minus 2 log 5. Now I'm going to distribute things out to free the x's from the parentheses. That gives me 2x log 2 minus 3 log 2 equals x log 5 minus 2 log 5. Now I need to group the x terms on one side and the other terms that don't involve x on the other side. So I'll keep the 2x log 2 on the left, put the minus log x log 5 on the left, and that gives me the minus 2 log 5 that stays on the right and a plus 3 log 2 on the right. Finally, I need to isolate x by factoring and dividing. By factoring, I just mean I factor out the x from all the terms on the left. So that gives me x times the quantity 2 log 2 minus log 5, and that equals this mess on the right. Now I can divide the right side by the quantity on the left side. When you type this into your calculator, I encourage you to type the whole thing in rather than type bits and pieces in, because if you round off, you'll get a less accurate answer than if you type the whole thing in at once. In this example, when I type it in, I get a final answer of about 5.106. In this equation, we have the variable t in the exponent in two places. The letter e is not a variable. It represents the number e, whose decimal approximation is about 2.7. Because there's already an e in the expression, it's going to be handy to use natural log in this problem instead of log base 10. But before we take the log of both sides, let's clean things up by isolating the tricky parts. We could at least divide both sides by 5, and that will give us e to the negative 0.05t is equal to 3/5 e to 0.2t. One way to proceed would now be to clean things up further by dividing both sides by e to the 0.2t, but I'm going to take a different approach and go ahead and take the natural log of both sides. So that gives me ln of e to the minus 0.05t is equal to ln of 3/5 e to the 0.2t. Now on the left side, I can immediately use my log rule to bring down my exponent and get minus 0.05t ln e. But on the right side, I can't bring down the exponent yet because this e to the 0.2t is multiplied by 3/5. So before I can bring down the exponent, I need to split up this product using the product rule. So I can rewrite this as ln of 3/5 plus ln e to the 0.2t, and now I can bring down the exponent. So that third step was using log rules to ultimately bring down my exponents. Now, ln of e is a really nice expression. ln of e means log base e of e, so that's asking what power do I raise e to in order to get e? And the answer is 1. So anytime I have ln of e, I can just replace that with 1. That's why using natural log is a little bit handier here than using log base 10. You can make that simplification. Next, I'm ready to solve for t. So I don't need to distribute here, but I do need to bring my t terms to one side and my t terms without t to the other side. So let's see, I'll put my t terms on the left and my t terms without t on the right. And finally, I'm going to isolate t by factoring and dividing. So by factoring, I mean I factor out my t. And now I can divide. Using my calculator, I can get a decimal answer of 2.0433. This video gave some examples of solving equations with variables in the exponent. And the key idea was to take the log of both sides and use the log properties to bring the exponents down.